Let's talk for a minute now about two-dimensional motions. We've talked about one-dimensional motion and using the kinematics equations to solve those problems. And now we want to think a little bit about two-dimensional motion. I throw something across the room. If it leaves my hand at the origin, then it follows a parabolic path across the room and lands on the other side of the room. It has a path that looks something like this. It leaves my hand at the origin. 1 unit of time later, it's got some position in space here as it's moving across the room. Then 1 unit of time after that, its position has changed some more. 1 unit of time after that, it would be roughly here. Then it would be here. And that's the top of its path. And now it starts its descent. So 1 unit of time later, it would be here, and then here, and then there, and then it's back to the same height that it started from. So if I were to connect these dots, it would have a curve that looks something like, we've got a parabolic path like that. The interesting thing here, let's take a look at what's happening along, this is, oh sorry, this is not time. Oops. This is x, and this is y, and that's the path that it takes, and those dots are spaced at equal time intervals. This is a motion diagram in 2 dimensions. Let's take a look at what's happening just in the x direction. The first dot, I guess I can number these. 1, 2, 3, 4, 5. Those time dots are spaced at equal time intervals like a motion diagram. So let's just look at the x motion. If we kind of look at the projection of these dots, if there was a light shining down on these dots, where would their shadow end up being? The first dot would be right there. The second dot, over here. The third one, the fourth one. So these dots are representing motion in the x direction. So what's happening in the x direction? It's moving at constant speed because those dots are equally spaced and they're at equal time intervals, so therefore the speed has to be the same. That kind of makes sense because what force is acting on this projectile as it's moving through the air? Gravity. What direction is that? Straight down. So there's nothing pushing or pulling or acting on this object in the x direction. So therefore it would make sense that its x velocity never changes. Now let's take a look at the projection of these dots in the y direction. So what do we have? We have dot 1, then 2, then 3, 4, and 5. That's on the way up. And on the way down, 5, 6, 7, 8, 9. They're obviously on top of each other. I've just spread them out so it's easier to draw them. And what does that remind you of? That's a motion diagram for throwing an object straight up in the air. So what that tells us is that we can think of these two motions, the x and the y, completely independently. We can break it up. If we were given some initial velocity, v initial, we can break that up into an x, I guess I should call it v initial in the x direction, and a y component. And what do we know about the x velocity? It's constant, right? It never changes. So in the x direction, the speed is always v0 sub x, never changes. In the y direction, there's acceleration due to gravity. So it's going to get smaller and smaller and smaller, and at 0.5 here, that velocity goes to 0. and then it starts increasing in the opposite direction. So if we were solving a kinematics problem, we could break it up into x motion and y motion. And you define your origin, and you define your positive directions, and then you fill in this chart, x initial, x final. That gives you the change in position in the x direction. V initial and V final in the x direction, acceleration and time. And if it's just projectile motion that we're talking about, then we know the acceleration is 0 and V final is equal to V initial. And in the y direction, you have a y initial and a y final. A V initial, oh, I should put subscripts here, sorry. These are x's over here. And these are y's over here. And you view them completely independently, except there's one thing that you can use to connect the two. Those have to be the same. It can't take longer for the object to get to its landing place in the x direction than it takes in the y direction. When the object gets to that landing spot, both the x and the y are there simultaneously. So the time has to be the same. So what happens with a lot of these problems, and you look at it, and at first you think, wait a minute, there's a piece missing to the puzzle. And then you figure out that you can use, there's something there, there's some extra information there, and you can solve for the missing piece, and then you can solve the puzzle. That's what makes these problems so much fun to do.